So I want to explain some of what I did with this problem. The first thing I did was I made folders, because if you look, I've got a ton of functions going on here, okay? And it just gets messy. So what I did was I had all this at first without this folder. I just went up here, I pressed the plus sign, and then I just did folder, add folder. And then it says, here's your folder, and you just put the name right there, whatever it is, name, and then you drag these into that. All right, so I've already made them. I did everything that was associated to the paraboloid here, f of x. I did f of xy. I did f of xy z equals c in brackets, so that whenever I move c, what that does is it says, okay, I want f of xy, but only when z is a certain value. So these are basically the contour lines going up and down the paraboloid. That's how you create that. Here's your first derivative with respect to x, your first derivative with respect to y, or partial of f with respect to x, partial of x with respect to y. Here is my gradient function. Got to put the 0 there, and when I graph it, well, first of all, there's the gradient there, and this is right here. This is a p. That's the point on the graph itself. And then I create the gradient vector. I called it h because I just liked it. And now here is the gradient associated to that point. It's the gradient of the paraboloid x squared plus y squared at the point. This points straight out, of course. Okay. Now I did similar to g. So here is my g function. This is the constraint function. This is actually the constraint when it equals to 4. Here's my g sub x, my g sub y, my gradient for g, and then I let I be that vector. And so that is there. So what I'm going to do, I want you to notice there is a vector that's coming off of here that's going to be in green. That vector there, I don't know if you can see it. Let me take this out. See this green vector, take out h. The green vector is the vector that is the gradient of g at the point. Okay? Now, if you remember with Lagrange multipliers, the gradient of f is equal to some constant times the gradient of g. And when I did the math here, basically, if you look, the gradient of f is here for the point, gradient of g for the point is there. These are the two gradients. These are vectors, right? So it looks like 1.6 comma 3.2 is equal to lambda times 1 comma 2. And so lambda would be 1.6. So sure enough, the gradient of g at the point is equal to some constant times the gradient of f is equal to some constant times the gradient of g. Now, if I go over here to this example, then it can't really draw vectors in regular Desmos, but I can draw a line that kind of represents it. And what I want you to notice is that the way I've done this is, here's my gradient for the constraint, and then the gradient for the function itself is 1.26 times longer.